visual sighting, infrared sensors, telescopic evidence. Now we have multiple sightings by multiple modes, and so the burden of proof has shifted.
When astronomers spotted 3I Atlas on July 1st, 2025, the discovery marked only the third confirmed interstellar object ever seen in our skies, following the mysterious passage of Oumuamua in 2017 and the comet-like 2I Borisov in 2019. What makes 3I Atlas particularly unsettling is its anomalous chemistry. This strange profile has revived the same unsettling questions that surrounded Oumuamua. Today, we'll explore what we know about this interstellar visitor and how Michio Kaku exposed a terrifying new truth about 3I Atlas. Let's start from the very beginning. The peculiarities of 3I Atlas. Officially designated C2025-1, 3I Atlas was identified by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, thus the name. The object's appearance marked the third confirmed interstellar detection after 1I Oumuamua in 2017 and 2IB Borisov in 2019. From the outset, 3I Atlas displayed a number of characteristics that set it apart. Astronomers determined its nucleus to be small, with an estimated size between 300 meters and 5.6 kilometers across, though Hubble Space Telescope imaging suggested an upper radius of about 2.8 kilometers. While modest compared to many solar system comets, the scale is sufficient to support a coma, or the gaseous halo produced as sublimating ices release material into space. More striking, however, is the object's path. Its orbit follows a hyperbolic trajectory, meaning it is not bound to the Sun by gravity and will eventually exit our system. This trajectory confirms its interstellar origin. What distinguishes 3I Atlas most dramatically is its composition. Spectroscopic studies conducted with the James Webb Space Telescope, or JWST, and ground-based observatories revealed that its coma is dominated not by water vapor, which is the norm for solar system comets, but by carbon dioxide. Researchers found a carbon dioxide to water mixing ratio of approximately 8:1, an astonishing result when placed against the backdrop of typical comets near Earth. In most cases, comets in our neighborhood display water as the dominant volatile, with carbon dioxide present in far smaller proportions. In 3I Atlas, the balance is inverted, suggesting that its formation environment was profoundly different from that of icy bodies around the Sun. Observers reported the presence of water vapor, carbon monoxide, and carbonyl sulfide alongside carbon dioxide. Additional detections of cyanide radicals and even atomic nickel were made using the Very Large Telescope in Chile, with nickel observed as early as July 20th, 2025, and CN confirmed by mid-August. The quantities of these gases were broadly comparable to solar system comets, but the overwhelming dominance of carbon dioxide remained the most glaring anomaly. Astronomers hypothesized that 3I Atlas formed near the so-called carbon dioxide ice line in its parent system, a region where temperatures are cold enough for carbon dioxide to freeze into solid form, but not so cold that other volatiles dominate. Another explanation could be that the body underwent long-term exposure to cosmic rays or other radiation that altered its surface and enriched its accessible volatiles. Either way, the object provides a direct window into conditions far beyond our stellar neighborhood. Further evidence emerged from pre-covery data obtained with NASA's Transiting Exoplanet Survey Satellite, or TESS, which had inadvertently captured images of the comet before its official discovery. Though the data did not allow for a clear determination of its rotation period, it suggested that the object may have been active as far out as 6.4 astronomical units from the Sun. This is well beyond the orbit of Jupiter. Such distant activity is unusual and implies that highly volatile ices like carbon dioxide were sublimating before solar heating could significantly affect water ice. This supports the argument that carbon dioxide plays a dominant role not only in the observed coma, but also in driving the comet's early outgassing. Next comes dating the object. Based on its trajectory and velocity of about 58 kilometers per second relative to the Sun, astronomers believe 3I Atlas originated in the thick disk of the Milky Way, a stellar population thought to be older than the thin disk that houses the Sun. If this is correct, the object could be more than 7 billion years old, older than our solar system itself. This means 3I Atlas has been wandering interstellar space for billions of years. Oumuamua baffled astronomers with its non-gravitational acceleration and lack of visible outgassing, leading to speculation that it was either a fragment of an unusual planetary body or even a technological artifact such as a solar sail. 2I Borisov, in contrast, behaved much like a typical comet, albeit one with higher levels of carbon monoxide. 3I Atlas falls somewhere between these two. While it exhibits conventional cometary activity, its chemical imbalance is just as puzzling as Oumuamua's motion. What makes 3I Atlas especially valuable to science is the opportunity for direct, sustained observation. Unlike Oumuamua, which was detected only after it had passed its closest approach to the Sun and was rapidly receding, Atlas was discovered early enough to allow coordinated campaigns by JWST, Hubble, the VLT, and other observatories. This coordination ensures that astronomers can build a comprehensive dataset combining optical imaging, infrared spectroscopy, and ultraviolet measurements. Such a dataset allows for direct chemical analysis and even hints at structural properties of the nucleus. Already, the robust detection of carbon dioxide dominance has reshaped expectations about the possible diversity of cometary bodies in the galaxy. If its peculiar chemistry stems from conditions near a carbon dioxide ice line, then its existence demonstrates that planetary systems form with different balances of volatiles, producing comets unlike any in our solar system. If, alternatively, its composition reflects billions of years of radiation processing, then it may be a harbinger of what awaits our own comets as they eventually drift into interstellar space. In both cases, Atlas is a scientific time capsule. Let's compare with the other interstellar objects before it. Back in October 2017, astronomers in Hawaii spotted a faint, fast-moving body that was unlike anything seen before. Using the Pan-STARRS 1 telescope at the Haleakala Observatory on the island of Maui, they detected an object that was quickly found to be on a hyperbolic trajectory, confirming that it was not bound to the Sun and had originated from outside the solar system. The object was later given the name 1I Oumuamua, a Hawaiian word meaning scout or messenger from afar. It was the first confirmed interstellar visitor to be recorded in human history. Oumuamua's physical characteristics set it apart from the comets and asteroids familiar to astronomers. At first, it was described as elongated, with early estimates suggesting a cigar-like shape, several hundred meters long. Later models suggested it might have been more like a flattened pancake, but in either case, its proportions were extreme compared to known solar system bodies. Its rotation was also irregular, described as tumbling rather than spinning smoothly. As Oumuamua passed through the inner solar system, it exhibited what astronomers call non-gravitational acceleration. In simpler terms, its trajectory deviated slightly from what was expected based on gravitational forces alone. Typically, comets display such behavior when they outgas or release jets of material that push them along. But in the case of Oumuamua, there was no visible tail, no detectable outgassing, and no other conventional explanation for the extra push. Further complicating matters was how the object interacted with sunlight. Oumuamua reflected light in unusual ways, displaying a higher than expected albedo, or shininess for a rocky body. At the same time, when scientists attempted to measure its thermal emissions, they found none, even though the object had passed relatively close to the sun. Normally, an object absorbing sunlight would radiate heat back into space, but Oumuamua seemed to absorb energy without releasing it in the expected manner. To explain the anomalies, some astronomers suggested that it was a fragment of a larger body, possibly ejected from its home system through gravitational interactions. Others proposed exotic natural explanations, such as a hydrogen iceberg slowly evaporating in a way that left little trace. However, one of the boldest claims came from Avi Loeb, a Harvard astronomer who proposed in late 2018 that Oumuamua could be a piece of alien technology. Specifically, he suggested it might be a solar sail, an artificial structure designed to use radiation pressure from starlight for propulsion, or perhaps a reconnaissance probe sent intentionally or accidentally by an extraterrestrial civilization. Loeb's arguments were laid out in his 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth. Among those weighing in on the debate was theoretical physicist Michio Kaku, a well-known popularizer of science and a professor at the City College of New York. Kaku described Oumuamua as not natural in both shape and behavior, emphasizing that it did not conform to expectations for a comet or asteroid. He speculated openly that it might be a probe or reconnaissance vehicle, perhaps part of a broader effort by an advanced civilization to explore other star systems. Kaku even raised the possibility that Earth had missed other such objects passing through the solar system, suggesting that Oumuamua could be part of a fleet rather than an isolated wanderer. In his view, the burden of proof had shifted. Scientists could no longer dismiss the possibility of interstellar probes as fringe speculation. Just 2 years later, in 2019, astronomers identified another interstellar visitor, this time with characteristics more in line with familiar comets. Named 2I Borisov, after amateur astronomer Gennady Borisov, who discovered it in August 2019 using a homemade telescope in Crimea, it provided a valuable point of comparison to Oumuamua. Unlike its predecessor, Borisov displayed a distinct cometary tail, outgassing water and dust in a manner consistent with solar system comets. Its chemical composition, measured with instruments such as the Hubble Space Telescope and the Atacama Large Millimeter-Submillimeter Array, or ALMA in Chile, showed the presence of common volatiles. However, it also contained unusually high amounts of carbon monoxide. The appearance of these two objects within such a short span of time was remarkable. Before 2017, no interstellar object had ever been conclusively identified. The discovery of two in just over 2 years suggested that such encounters might be more common than previously thought. This realization spurred efforts to improve detection capabilities. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, scheduled to begin operations in the mid-2020s, are expected to dramatically increase the number of detected interstellar visitors by scanning wide swaths of the sky with unprecedented sensitivity. By the time 3 IATLAS appeared in 2025, the stage had already been set by the first 2 interstellar visitors. The scientific community had learned from the shock of Oumuamua and the familiarity of Borisov that interstellar objects are both more common and more diverse than expected. The anomalies of the first object and the comparative normality of the second created a framework for interpreting the peculiarities of the third. Now, the scary part: extrapolating Kaku's insights to 3I Atlas. When Michio Kaku weighed in on Oumuamua, his emphasis on the not natural character of its motion, shape, and unexplained acceleration reflected a readiness to consider possibilities beyond standard astrophysical models. Extrapolating those insights to 3I Atlas reveals striking parallels in how we might interpret the anomalous chemistry. In most solar system comets, water ice sublimation drives activity when they approach within 3 astronomical units of the Sun, with carbon dioxide and carbon monoxide playing secondary roles. But 3I Atlas showed early signs of activity at around 6.4 astronomical units, almost at Jupiter's orbit, suggesting that its volatile budget is not only inverted, but also more sensitive to low levels of solar radiation. For a body estimated at 300 meters to 5.6 kilometers in diameter, this dominance of carbon dioxide raises pressing questions about its formation environment. Kaku's logic with Oumuamua was that deviations from expectation, when unexplainable by known natural mechanisms, invite alternative interpretations. Applied here, the same reasoning points to the idea that such an alien chemical fingerprint could either reflect an exotic birthplace in the thick disk of the Milky Way more than 7 billion years ago, or perhaps deliberate engineering of its volatile content for reasons beyond our current grasp. One of Kaku's most provocative suggestions after 2017 was that Oumuamua might not have been a lone interstellar wanderer at all, but a part of a fleet of probes, most of which slipped by undetected. This speculation was built on the statistical improbability of detecting one such object given the vastness of interstellar space. If even one is observed, he reasoned, countless others must be crossing silently through. The discovery of 2I Borisov in 2019 and now 3I Atlas in 2025 lends weight to the idea that interstellar visitors are not once-in-a-lifetime events but recurring phenomena. Extrapolated further, Kaku's fleet hypothesis could be reinterpreted to mean that we are not merely seeing random representatives of distant cometary reservoirs, but perhaps a coordinated, or at least non-accidental pattern. When only one interstellar object had been catalogued, it was defensible to dismiss its oddities as singular. But with 3 objects, each presenting unique and confounding anomalies, the argument that such bodies are simply natural curiosities grows weaker. Oumuamua accelerated without detectable outgassing. 2I Borisov looked conventional but chemically enriched. 3I Atlas exhibits chemistry alien to our solar paradigm. If carbon dioxide dominance is indeed a marker of an unusual environment, then studying its isotopic ratios and outgassing patterns may reveal whether it formed in a primordial disk rich in carbon dioxide ices, or whether its chemistry was artificially reset. Carbonyl sulfide and hydrogen cyanide, both detected in its coma, are particularly intriguing. On Earth, these molecules have roles in prebiotic chemistry. Thus, Atlas could carry a record of processes relevant to life's origins elsewhere. Kaku frames such intersections as the point where speculation becomes duty. Moreover, the very longevity of the object, likely over 7 billion years old, older than the solar system itself, reinforces its role as a witness to galactic history. An artifact that, ancient, carrying an anomalous chemical profile, could either be a preserved natural relic from the earliest epochs of the Milky Way or something intentionally enduring, engineered to survive stellar migrations and galactic tidal forces. Kaku's insistence that probes might be scouting us gains a new dimension when applied to Atlas. The pattern across interstellar visitors is now becoming too pronounced to ignore. Oumuamua forced astronomers to confront a motion they could not explain. 2I Borisov showed that not all visitors are suspicious, but even that control case was chemically rich in carbon monoxide compared to local comets. 3I Atlas now presents an inversion of expected volatile dominance. But that's not all. Shocking claims and theories. Like its predecessors, Atlas is on a hyperbolic trajectory, meaning it is not bound to the Sun and will eventually leave the solar system. It is passing through. For some, this means that it is an alien probe. Harvard astronomer Avi Loeb argued that Oumuamua, the forerunner of Atlas, might be a solar sail or some kind of artificial construct. In Atlas' case, theorists note that carbon dioxide sublimates more efficiently than water ice at greater distances from a star, meaning it could theoretically serve as a designed fuel source. A probe optimized for long-range propulsion might deliberately use carbon dioxide for maneuvering, leaving no signs of water vapor. The additional presence of gases like carbon monoxide, carbonyl sulfide, and cyanide raises the question of whether these are simply products of exotic chemistry or carefully engineered mixtures. A related idea is the scouting fleet theory, which draws on the arguments of physicist Michio Kaku following Oumuamua. Kaku emphasized that such interstellar objects should not be seen as isolated oddities. Statistically, if humanity has observed 3 in less than a decade, countless others must have slipped past undetected. He went further, speculating that we might be witnessing members of a larger fleet of reconnaissance vehicles. Then there's the cosmic warning theory. Less rooted in astronomy than in philosophy and speculation, this idea suggests that interstellar objects are messages or markers left by advanced civilizations. Because they arrive and leave on hyperbolic paths, they appear purposeful rather than random. In contrast, the astrobiological perspective offers a more grounded approach. Instead of assuming engineering, researchers examine what kind of planetary nursery could create such an object. The key lies in the concept of the carbon dioxide ice line, the distance from a star where carbon dioxide can condense into solid form. In the solar system, this lies far beyond Saturn, where water ice typically dominates comet formation. If Atlas originated in a system where the carbon dioxide ice line was more prominent, its chemical profile may be a natural relic of that environment. Since the object likely hails from the thick disk of the Milky Way, and may be over 7 billion years old, it could preserve ancient chemistry from the galaxy's earliest planetary systems. Intriguingly, molecules like carbonyl sulfide and hydrogen cyanide detected in its coma are tied to prebiotic chemistry on Earth, suggesting that Atlas might carry clues to life's potential origins in alien systems. Looking across the short but significant record of interstellar visitors, a pattern of anomalies emerges. Oumuamua defied expectations with its strange shape, reflectivity, and unexplained acceleration without visible outgassing. 2I Borisov looked more like a traditional comet, but was chemically enriched in carbon monoxide. Now, 3I Atlas adds the most extreme twist yet, with its carbon dioxide-dominated composition. Each object has been different, and all resist neat classification. Kaku's statement that the burden of proof has shifted resonates strongly here. Repeated anomalies in less than a decade demand serious attention rather than dismissal. Just as Galileo's 1610 discovery of Jupiter's moons forced humanity to reimagine its place in the cosmos, the succession of interstellar objects compels us to rethink the solar system's boundaries. If these visitors are natural, they showcase the diversity of planetary systems and highlight environments far stranger than our own. If even one is artificial, the discovery would signal that humanity is already participating in a galactic dialogue stretching across time and space. Either way, the stakes are extraordinary. For now, scientists and the public grapple with competing interpretations. The alien probe hypothesis remains unproven, but compelling given Atlas's anomalies. Ultimately, 3I Atlas reinforces the reality that the solar system is not isolated. In just 8 years, 3 confirmed interstellar objects have entered our neighborhood. As Kaku warned about Oumuamua, we must prepare for the possibility that such objects are not merely cosmic debris, but scouts, probes, or even ancient messengers. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.